Today, two things. So we'll first talk about the rotating coordinate system, and you might think like, geez, haven't we had enough pain already? Like, why do you have to talk about this? But this is really it's the mental model that you use. It's a simplifying mental model that you use to think of how the MRI signal works. And it's kind of the intuitive model that the MRI physicist would use, and it's supposed to help. So that's the idea. It's supposed to make it easier to understand what's going on. That's really the goal here. So it wasn't designed to sort of make life difficult. It was actually designed to make life easier. And then we'll sort of intuitively talk about receptive field polarization. That's essentially how does the B1 field get into the protons, and how does it come out of the protons? Just sort of talk about it, just to get that basic geometric idea, and then we'll do the equations for it on Friday. So that's the plan for today. So let's start off with the not rotating coordinate system again. So the not rotating coordinate system, the idea was that I drew this up before, but we'll do it again. So the idea is you've got the B0 coming up here. So that's the B0. And then the B1, which, like I said, it's all part of the full B vector, has something added on to it, and so here's the B1 field. This guy is rapidly moving around. So this guy is the B0 vector. That one's caused by the main magnet, and then this guy is the B1. That's caused by the RF coil. And those things basically just add to each other. So if we do tip to tail and add those two guys to each other, that's the actual B vector. This plain B vector. So if you happen to have the RF turned on at the same time, the B0 is always on, but you turn on the RF, and it's rapidly moving this guy around in a circle. It's much smaller. The magnetic field from the B1 coming from the RF coil is much smaller component than this very large B vector, but it's basically wiggling the B vector around. And then we have our M vector, which is also a lot smaller than the B vector, but I'm just drawing it here as if it was big. So that guy is the M vector, and that's the local magnetization that's coming from the alignment of the precessing protons in the little chunk of the brain. And then we broke that up into three different parts. We broke up the update of that into three different parts. So the first part was this precession part, and then there was we'll put it back to here, then there was a T2 decay part that was perpendicular. It's always perpendicular to that precession update. And then there was a T1 regrowth. That's heading back to equilibrium magnetization. And that one was also perpendicular to those other guys. Everybody's perpendicular to everybody. And then that gave us the full update vector. So here is the full update when we add those three vectors together. And so this guy was the dm dt, and that was broken up into the m cross product with the b, and that was this guy, and then minus the mxi plus myj divided by t2 minus that guy was the t2 decay, and then we had minus mc minus mz0 times the k vector over t1. So that was it's a minus, but because this term in here is negative, because mz is always less than, at most it could be the same as mz0, but it's always less. So it's a negative of a negative, so that one expands. And so that guy was right there. Okay, so that was our basic picture of, so there's that part, and this guy, and that guy, and that guy. Now, if you just look at this, you can see, well, there's kind of a world of pain in here, because this thing's wiggling around, and then you've got this guy's rapidly going around, possibly at a different speed. So just consider like all the different bad things that can happen. Like the precession might be happening at a slightly different rate than the B1 field. That happens all the time, every day, every single RF pulse that's happening. And so then how do we sort of put those two together? They're two rapidly changing fields that are slightly out of sync with each other. And then, everything's changing size. So for that purpose, we introduced the rotating coordinate system. And this is really the way that the people typically kind of think about what's going on. And so the way to do this is we start off with what's called, the laboratory frame. And so here's our B field, and then we've got our M going around it. And here's the coordinate system. So there's our 3D coordinate system. I'll take out some of those other ones, so take out this guy, it's a little confusing. Okay, so that one's called the laboratory frame. That's what we drew here, because that's actually what's really happening classically. So there's the total B and the total M. So to move to the rotating frame, all we do is just assume that we're spinning around at the same speed as the precession. So the precession's going around in this direction, 120. For our magnet, we're like 2.89 Tesla, so it's 123 megahertz. 123 million times a second. So if we spun ourselves around at that rate, what would happen? So what would happen is we would just stop this M vector in its tracks. So here's another coordinate system. So the M vector would just be stopped in its tracks. So what does that mean? So that means that in the rotating coordinate system, it's as if there was no B0. So M is stopped. So the M vector is stopped. And so B0, B0 equals 0. It's just like we turned it off. That magnetization is still there. It can just be whatever, whatever it is. But notice that if we happen to have B1 exactly at the same rotation frequency as the M vector, then B1 is also, it's not stopped, but, it's not 0, but it's stopped. So there's, so it stops the M vector in its tracks, doesn't change the length of it when we're spinning around. That's equivalent to saying we just turned off the B0, no B0 anymore. But it also stops the M vector. And so it stops it stops the B1 vector caused by the RF coil. So this guy is RF coil. RF transmit. That's the RF coil sending radio waves into your head. So it stops that guy too, because that one is also rotating around at very high speed. So what's the point of this? Like conceptually, what's the point of this? So conceptually, the point of this is that we can still use. So remember when he said that this B up here in the Bloch equation included everything. It included the B0 field, but it also included the gradients, which are messing with the B0 field, and it also included the RF coil B1 field, which is perpendicular to those, and that's rapidly changing. All those were in there. So we haven't gotten rid of the B1 field, but now we can think of how it's affecting things using that same M cross B equation. And so let's draw the M vector. So there's the M vector. And now we're going to draw the B vector. So here's one possible B vector. There's many B1 vectors, many different ones, but let's just look at this. So here's the M vector, and here's the B1 vector. So say we're stimulating at the same frequency as the M vector is rotating. So this guy won't be moving, and the M vector won't be moving. So now what we can do is we can still apply, this is why it's a conceptual simplification, we can still apply M cross B. And so what is M cross B? Well, it's just, you take the B field and you draw a plane through through these two vectors. These two vectors will define a plane, the B1 and the M, and then perpendicular to that plane will be the cross product, and that cross product will then allow you to see how that B field is going to affect the M field. And using the right-hand rule, there's another little trick that some MRI physicists use. If you, let me see if I can do it. I gotta use my left hand. So if we go into okay, that's about right. So if you move your hand as if you're holding a screwdriver, and you're trying to screw the screwdriver in, that's the direction the M field is going to go. So move your hand, put your hand at the end of the B field, and then screw in a screw with your right hand, and that's the direction. That's the same thing as the cross product, but it's just another way of sort of like you're screwing in you're screwing in the m vector and moving it in this direction. So that's the direction it would move. You could also do it with the other right-hand rule for sweeping your fingers from the tip of your fingers from the direction of the M to the B, and then your thumb will point in the direction of the cross product. So that's an advantage, and this is basically the way that people think about what's going on in the MRI magnet. They think about it as it's a stationary vector. We're flipping a stationary vector, and then this stationary vector is slowly recovering and going up, and they don't think about the rapid oscillations. Now, something might have disturbed you, like what does it mean for this guy to point in different directions? Or what does it mean? I drew the B1 as if it was, coming out of the x-axis here. So that's the x-axis. Here's Z, 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 and here's Y, Y, Y. So I drew it coming out of the x-axis. Why did I do that? And what does it mean if it was coming out of a different axis? So, because you can see the B field could point, in any direction, around this. Sorry, I always messed up my mirror image. Yeah, so there we go. Yeah, so it can point anywhere in the xy plane, but also the m vector. The m vector can be anywhere in the xy plane. It could sort of be, it could be right along the y-axis, or it could sort of, rotate out toward the x-axis, or it could be along the negative x-axis. And what's that? What does that mean? That actually has a meaning, and the meaning is the phase of the rotation. So the direction that it points along the xy plane. So say this m vector happened to be right over the y-axis. Okay, it just happened to be right over the y-axis. That reflects a certain phase of the rotation. And so what is the phase of the rotation? It means that this requires that we define what time t equals 0 is. And we'll explain what does that. But if you say we start up the oscillation at time t equals 0 with the m vector right over the y-axis, and then every 123 million times a second it'll come back, and 123 millionth of a second later it'll be over the y-axis again. But we could distinguish that from a different situation in which we start up the oscillation pointing out a little bit. So say it was pointing out a little bit toward the x-axis. It's still going around 123 million times a second, but it's like a quarter cycle ahead. So you could imagine two different situations, two different m vectors, one of which is a quarter cycle ahead. They're both going 123 million cycles per second, but one's a quarter ahead. That's what the phase means. And it turns out MRI is all about the phase. That's all there is. It's pretty much just the phase. So we're gonna hit this hard over and over again. But that's the meaning of the B1 field. And so you could imagine for the B1 field, you can imagine, say the m vector's starting at time t equals 0 on the y-axis and it's going around. Now you could imagine when we apply the B field, we could start the B field up at various times. So we could start the B field up in sync with the M field, or we could sort of have it a quarter cycle ahead of the M field. So the B field could be in some arbitrary direction around this xy plane, just like the M can be in some I just drew it on the x-axis, and on the y-axis it doesn't have to be there, it could be anywhere. But the advantage is, no matter where it is, those two vectors will define a plane, and when we take the cross product, we'll, using this equation here, we'll get the place it's going to go to next. This is the place it's going to go to next. And so that equation will work no matter what the phase of the B1 is, and no matter what the phase of the M is. So that's so this is mental model basically that just tries to simplify our world by sort of moving to the rapidly rotating coordinate system. And I'm going to go over this again when we talk about off-resonance excitation, but let's see how we could sort of use this mental model to sort of help us think about a complicated situation. And the complicated situation is what if what I mentioned before, what if we apply the B1 field at a different frequency than the M is going at? Turns out this is happening every single RF pulse. This happens. So what does that picture look like, and how do we sort of, how can we sort of conceptualize that picture? So here's the same y-axis, x-axis, and z-axis. So now let's say we've set our rotating coordinate system, which is going to be our B1 frequency, slightly off of the actual M rotating frequency. So here's the M. So here's the M vector as we had it before. So our M vector is now slowly rotating. So I forgot. Before I do that, I should annotate this guy. So B1 is stopped. But this is what I just said in words. But M cross B still works. And so what does it do? It causes precession around B1 axis. That's what this is, what I drew there. So instead of precessing around the B0 axis, this is precess around B1. And then we talked about phase. Phase in XY plane. And that has to do with where you consider time t equals 0 to be. Okay, so now back to this more complicated situation where we've set the rotating coordinate system slightly different than the than the M, than the actual sort of speed of rotation of the M vector. And so what's going to happen? Well, the M vector is going to start to rotate around because we're at the wrong frequency. So if rotate chords off, M slowly rotates. Now it's way slower than it would be, from the B field, because if we're off by like a part per million, we're talking about like we're off by a part per million, and so it's a very slow rotation compared to the 123 megahertz rotation. But what is that equivalent to? That's equivalent to having a little B field. Now it's way smaller than than our original B, but it's like we'll call it a B effective. So it's a small B effective, just EFF. So it's as if there was a small B field. So that guy, which is causing some precession some slow precession because we've set our coordinate system off. Now you're wondering, like, why would you set the coordinate system off? Was the whole point to stop it? But say we set the coordinate system off to the frequency of the B1 field. So say this is a case where this guy's going around at a given frequency, and we're stimulating with a B1 frequency that's different than this guy, and we're setting the rotating coordinate system to what we're stimulating at. So our B1 is going to be stopped. So there's our B1. So this is our B1 vector. So that guy's stopped. But now, how can we sort of conceptualize what we're going to do to the M vector? And the way we conceptualize that is we basically add these two vectors together. So, and we get another vector like that, sort of coming out at you. And we'll call that guy the B effective, the total B effective. So that was like the B1 effective. Let's relabel that. So this guy is the total B effective. I'll write it out. That's this guy. And this is the pseudo B0. This guy. Because we set the rotation frequency of our rotating coordinate system wrong. Okay, so after all that, what's going to happen? Well, what we're going to do is we're going to cause this M vector to precess around the effective direction rather than the B1. And so it's a little hard to draw, but this guy is going to precess around a plane that is not going through the y-axis. So this guy it's going to precess sort of in the same general direction, but it's basically going to come out of the y-axis. So in this case, this vector was just aiming straight toward the y-axis. In this case, it's actually kind of aiming out. It's coming out at you. It's changing its phase. That's basically what it's doing. And so this is, we'll come back to this, but this is a way of trying to sort of, you've got a primate brain. It has a really good visual system. We've got to squish it down into some simple three-dimensional picture that we can sort of understand at frequencies that we can understand. And so that's the reason for the rotating coordinate system. Okay, so we'll come back to it, but this just gives you an idea why people are always talking about flipping the magnetic field vector. They're just conceptually thinking in this rotating coordinate system where you just flip the magnetization down and it comes back up, and maybe it decays away and then it goes back up, and you don't have to worry about all the rapid motions. Okay, so are you conceptually simplified now? So that's the rotating coordinate system. Okay, any questions about that? You can see we go over the Bloch equation over and over again. Okay, any questions out there? Yeah, forgot to put, so slow precession around B effective. let's this guy, slow precession around be effective. So none of the homework, there's no M cross B in the homework. It's mainly just about the decay. But it's important to sort of get a feel for this, because like I said, and get a feel for this whole idea of the phase, because that's pretty much how the whole thing works. Okay, so that was the rotating coordinate system mental model, including a little off resonance, which we'll come back to. So now let's talk about the actual sort of polarization of the radio frequency field. And so polarization just sort of means some kind of direction, and there's different kinds of polarization, you know, like a Polaroid filter. If light waves are coming in and they have a certain direction to the electric and magnetic fields of the light wave, then you can put a Polaroid glasses on and it will block them depending on what angle you rotate the glasses. So that's like a linear polarization, but you can also have a circular polarization where the light waves are, the fields of the magnetic fields are kind of rotating around in a spiral. And so let's talk about how we can do both of those things with the RF coil. And so we'll start off with a linear RF coil, which is the simplest one. So let's make an extra large bore here. Let's see, it's about here. That's a much bigger bore. I compressed the magnet a little bit. Okay, here's our magnet going in. Nice big bore so we can draw a big person in there. And so we've got to draw an ugly person in there. There we go. Okay, there's a big head in there. So how do we stimulate and record? And so the way this works is, one way of doing it is we could just put a coil like this next to the person's head. Okay. So there's a little coil like that next to the person's head. And if we run current through that coil and rapidly change it back and forth, like, put positive current in and then quickly change it to negative current, back to positive current, that's going to make an oscillating magnetic field. And how does that work? Again, we have to use the right-hand rule to predict what direction the magnetic field generated by that current is. And so what you want to do is, if we have the current, say, coming this way, my thumb is the current, and then my fingers will indicate what direction the magnetic field is. And so the magnetic field will be coming out at you if the current is going this way. But if I quickly reverse the current and make it go the other way, make it go this way, then the magnetic field is going to be coming away from you. And so if I put a sine wave, a sinusoid into the magnetic field, what will happen is you'll get a magnetic field that's coming out at you this way, like this, and then a half of 123 millionth of a second later, the magnetic field will be sort of going this way, sort of away from you. So that's a linear polarization of the field. And it turns out that's good enough to stimulate protons. Now, how are the protons set up? Well, we said the B1 field is along the direction of the Bohr, and so that's the direction of the B0 field. And so what's going to happen is the protons are going to be either aligned or misaligned with the magnetic field, like that. And so they'll be rapidly rotating around in that XY plane. Like that. So now, why did I put the XY plane there? Well, because we can't, when you actually sort of put current through a wire to generate a magnetic field, you have to do it relatively rapidly in order to generate a decent magnetic field. The current has to be, the change in the voltage of the local voltage of the current has to actually be very, very rapid. And when you're thinking about this, when you're thinking about sort of the protons generating a magnetic field that's changing, causing a current, or just the converse of that, current in the coil causing a changing magnetic field. Those two, you should think of those things as kind of, sort of symmetrical. So like I can put current, a moving current into the coil, and that will generate a magnetic field, or I can move a magnetic field through the coil, and that will generate a current. And so that's, that's basically, record and stimulate. So I can either have the protons change their magnetic field very rapidly through the coil, that generates a current, or I can just put a current into the coil, and that will generate a magnetic field. And so it will be the same situation here. Now, why we only deal with the XY plane? It's because you have to actually move magnetic fields or current around at a very high speed in order to actually have a substantial effect here. And so if the Z component, which is the regrowth, the T1 regrowth, that's too slow to actually generate any signal. And so even though the actual bulk magnetization might be, something like this, it might be actually rotating around like this, we only get the XY component of it in our signal in the coil. So we don't get any of the Z component. And so that's why we always just refer to the XY polarization. So let's just talk about our linearly polarized RF, just from one coil. And before I do that, one last thing. So why did I twist the wires? Wires are twisted here. There's a reason for that, which is that if you think about current going through this twisted wire, and then going through the coil, and then coming back and going through the other twisted wire, what happens if we sort of calculate what the magnetic field is that we generate from the current in those two wires, they'll exactly cancel each other out. Because in one case, the current will be flowing this way, generating a magnetic field, but the same current will have gone through the coil, and it's now going the opposite direction in the other wire, and that will generate a magnetic field that will cancel it out. And so this is a way of only causing this device to generate a magnetic field here and not in the wire. But it's also a handy way of stopping any magnetic fields from actually inducing currents in this part of the wire. Because if I move a magnetic field, rapidly moving a magnetic field through this twisted wire, I'll generate two opposing currents in the wire which will cancel each other out. And so that's why it's twisted pair. So that's like if your Ethernet wires are accidentally generating magnetic fields or accidentally picking up magnetic fields, how do you sort of shield them? They're always, that's what it means, twisted pair. So you just twist the wires in there, and so the signals going back and forth cancel each other out. So that's why they're always twisted. Okay, so back to the linearly polarized RF field. So what's an equation for this? So this is the B1 field as a function of time, and so that guy's a vector, and so the simplest kind of thing we could do is just take the amount of the B1 field, so that's just a scalar amount, and then multiply it by a cosine. And that's the frequency of how rapidly we're changing times a point in time. So cycles, this is radians per second times seconds equals radians, and then we take the cosine of that, and that will give us an oscillating signal. That's still a number. So that's a number. This is just the amount. That's another number, not a vector, and then we multiplied it by the x vector, or the I vector. We'll just put x here. And so what will that generate over time? That will generate something that is basically, you got a big B0 field, and then on top of that we've got this little B1 field. Sorry, put a 1 in there. Yeah, B1 field as a function of time. So this guy is just a mount, how strong it is. This guy is another number. It's a cosine, so a cosine sort of looks like that. Not a terrible cosine. Draw a slightly better cosine. So there's 0 and 360. So a cosine looks like this. There we go. That's 0, 360. And this guy's a vector, and so when we multiply those two numbers times a vector, we get a vector, and that adds together to give us our, so here's our B0, and here's our B1, and this is B0 plus B1. So it turns out if you do that, that's good enough to stimulate protons. It's to line them up, and it's kind of like if you had somebody, you're trying to sort of make somebody go around in a circle, and instead of just actually pushing them in a circle, you just push them in a single direction. So it's kind of a little strange how that works, but that will actually work. So even though we're only pushing the protons kind of this way, just kind of into the board and out of the board, it will actually cause them to line up and rotate together with each other. But you might think, well, wouldn't it be better if we sort of pushed them in a circle? And so it would be better if we pushed them in a circle. And so how do we do that? Well, one way of doing it would be to put another coil. There's a lot of different ways of doing it, but we could also put another coil over the top of the person's head like this. So say we put another coil like that. And that coil, the plane of that coil was at right angles to the other coil. So if we did that, and then we put a signal that was offset in time into that other coil. So say we put a sine into this one, and put a cosine into this guy. So now what will happen? So they'll be off by a quarter of a cycle, and in that case, what you'll do is right in the head, you'll induce a magnetic field. Instead of just going in and out, it will be a magnetic field that's actually sort of going around in a circle. And so how do we write that out? So that would be, so here's our B1, linearly polarized. So here's our B1 circularly polarized. And that's just going to be, it's a vector, but now it's a vector that can go more than just the x direction. And so it's going to be the B1 amount times the cosine as before. So there's one coil. So that's the amount of that coil times the x vector, and minus or plus, depends on what direction we go. So the sine of the same thing times the y vector. So basically, there. So now we have a vector that will be rotating around in the xy plane. And if you look at this relationship, what will happen is when the current is really high in the cosine coil, so think of cosine and sine. Draw it out a little bit bigger. So here's the cosine at 0 and 360, and then here's the sine. So now what will happen is when the current is really high in the cosine coil, it'll be 0 in the sine coil, and then you'll get to a point where they're both the same. That will be like a 45-degree vector. Then the current will be really high in the sine coil and 0 in the cosine coil, and so then you'll be pointing along the direction of that coil. And then as you keep going on, it'll just rotate all the way around through 360. And so how do we write that out? We typically write that out as a complex number. So you write that out as B1 times e to the minus I. The minus is that guy. Omega 0 t. So it's that complex business again. And so how do we think about this? We think about this as whenever we see e to the I angle, the way we think of this is we've got this linear variable, that's an angle, that's a linear variable, and then that e, when you put something up to e to the I, the output you get out of it is a circular variable that wraps around on itself. So the output of that guy is circular. Now we often have a minus in there, and what's a minus? Well, you can think of, e to the minus I theta is equal to e to the I minus theta. And so it just means a negative angle. And so if we think back to our coordinate system here, so our complex number, this specific, so it's a circular variable amplitude 1. So a complex number can be any amplitude, but that thing is always indicating an amplitude of 1 when you see that e to the I business. And so basically, what is the length of this? This is basically just the cosine of this angle. And what's the length of this? It's just the sine of that angle. And so what is e to the minus I? It's just using a negative angle. That's all it is. So it's not mysterious. And so so what happens is, so this guy, this distance here is the cosine. So this is a more compact way of writing out this mess. So this guy always has a length of 1. So it just indicates what the angle is pretty much. And then you scale it by multiplying it by the amount. Now, one of the things to definitely keep separate in your mind is the difference between e to the I business, or minus I. The I is the critical part, whether it's plus or minus, versus like e to the minus t2. So, because we just had a whole bunch of stuff about, so say you've got an equation, and these are often mixed together in an equation, and it's important to distinguish them conceptually. So you got like e to the minus t over t2. So whenever you see e to the minus real number, because t is a real number and t2 is a real number, then what do you think? You think this. That's what you think. It starts at 1, falls off. So when you see that, that's what you think. That's your mental picture. But you might often have, right next to it multiplied by, e to the minus I omega t. And when you see that, you don't think of a fall off. Instead, you think of something completely different. And what do you think of? You think of rotate. So this means rotate. Rotate without scale. So that's a completely different operation. Unfortunately, the mathematical notation looks nearly identical. It does behave identically, so if you're taking a derivative or doing something, you can just treat this as if it was a regular exponent. So that's the reason why people have done this, have set up this sort of minefield of this being completely different than that. But conceptually what's going on is whenever you have e to the minus real number, you think that. E to the minus real number, whatever the real number is, it's going to be an exponential decay. Whenever you see e to the minus or plus I, you think something completely different. You think we're multiplying this real number by a complex number. And what does that do? How do you multiply complex numbers? Remember, you multiply complex numbers by multiplying their amplitudes and adding their angles. So this is, mult by complex. And what is that? That's mult amp add angles. But since the amplitude is 1, it's always 1. This is 1 here. And this is 1 here. Since the amplitude is always 1, then we're multiplying by 1, so it's not changing the length. And then all we're doing is adding the angle. So it just takes whatever the angle was of this pre-existing complex number and adds on to it, or subtracts from it if you've got a negative. So we're going to be doing stuff on Friday that just looks just like this. We've got some decay terms. This guy's a decay term, exponential decay terms. Always e to the minus real number is always starting at 1, and then it goes down. E to the minus or plus I times an angle. Remember, this guy's an angle here. Angle. So whatever that angle is, we're just going to rotate this complex vector and not change its length. So just rotate it to a different angle. Okay, so how was that? Any questions Questions about this? So if we've got these two coils in here, and they've got a sine and a cosine going into them, offset by a quarter of an angle, what we'll do is we'll cause instead of a vector just sort of coming out like this, it's going to cause the vector to rotate around inside the brane. And the same thing is true from the recording side. So if you have a vector that's rotating, the magnetic field vector that's rotating around inside the brane, what is it going to do? Well, it's going to make a cosine signal come out of this coil and a sine signal come out of this coil. And so it works the other way around. So we can either sort of inject a cosine and a sine and cause a rotating magnetic field inside the brane, or there's a rotating magnetic field inside the brane that will cause a cosine and a sine to come out of these coils. Okay, so any questions out there? So we'll talk on Friday just like what the signal looks like. Like you might wonder, like, what if the coil what if it wasn't straight? What if it was at an angle, or what if it was kind of like this way? Or you can see there's some more complexity to try to sort of figure out what's going on. But it's not too hard. Once you got this basic idea in your head about, inject a current that makes a magnetic field inside the head, make a changing magnetic field inside the head from some protons that makes a current. Once you got that in mind, you're all good. Okay. Any questions? Even ones that go back to the very beginning of the class, okay? Sort of clear? Not too bad. Everybody's very quiet. Stunned silence. Okay. We'll talk about how do we actually, how can we sort of write a simple equation that describes what signal is going to come out of one of these coils. It's not very much. It's basically very similar to this. Okay.